pleasure of hosting Atakan Aral from University of Vienna in Austria. He is an assistant professor of information systems engineering there. He received his PhD from Istanbul Technical University in 2012 and was a postdoctoral fellow at TUVN, again in Austria. And his research focuses on optimizing resource utilization and placement at the network's edge for data-driven workloads. We are very happy to host you today, Atakan Hocam, and stage is yours.
Thank you very much. I received my PhD in 2016. I'm not.
Oh, sorry,
I'm not that old. Just kidding.
I've seen the master's degree. Sorry.
Yes, no worries. Hello everyone. Thanks again to organizers for the invitation. And today I will talk about Edge AI for the specific case of remote monitoring. I will talk about what I mean by remote monitoring very soon. And this work was done in University of Vienna, but also in my previous affiliations at the Umeå University and Technical University of Vienna, with the generous funding from listed bodies below. So I will talk mostly about environmental monitoring. According to UN definition, it is a tool to assess environmental conditions and trends, to support policy development and its implementation, to develop information for reporting to national policymakers, international forums and the public, and most relevant for us, to achieve real-time decision-making. And this part is enabled by recent rapid advancements in machine learning technologies and Internet of technologies that allow large amounts of data. And what I mean by remote monitoring or remote environmental monitoring, because it might be confused with remote sensing, which is a completely different thing. Remote sensing means using, for example, satellite images to infer about environmental phenomena without in situ sensors. In our case, we are not using remote sensing. We use in situ sensors. So if we are monitoring water, there are sensors within the water. But it is remote because of two reasons. Because we are collecting data in geographically remote regions. And this has the challenge of lack of reliable energy availability and network connectivity. Some examples are shown here. I will mostly talk about water pollution monitoring. Another aspect of remoteness is using connected IoT system to gain real-time insights remotely. So our facility is somewhere else, in contrast to traditional environmental monitoring where the water samples are collected and analyzed in lab. And this requires, of course, sensing equipment, communication equipment, and processing equipment. And processing equipment can vary from small micro computers like Raspberry Pis to massive data centers. Here there are some examples of remote environmental monitoring from my latest paper. I will give a few examples from public projects or nonprofit initiatives. And I will not go into the details. I will give the reference to this paper if you are interested. This one is a global environment monitoring system for air by United Nations. This is another air quality monitoring for city of Helsinki by the University of Helsinki. This is a Swain project by me for water quality monitoring, and I will talk about this project, so I will come back to this slide anyway. Another water quality monitoring project is Waterline, which uses, interestingly, crowdsourced data. Again, I will give the reference to find further details about it. Other type of environmental monitoring is seismic monitoring. This is European Mediterranean Seismological Center with more than 2,500 sensors all around Europe. There is also an avalanche monitoring system in Switzerland, IMIS, Intercantonal Measurement and Information System. And maybe the largest and most distributed monitoring system in the world is CTBTO, which is used for monitoring nuclear tests. So nuclear tests are banned according to the agreement, international agreement, and CTBTO's role is to monitor that or check that no one is actually conducting nuclear experiment. And to do that, they have a worldwide sensor network. They have sensors in both poles, rainforests, all around the world, basically, almost homogeneously distributed all around the world. And all these examples are remote cases, so that the sensors are deployed in, as you can see, non-populated areas all around the world. This is a brief summary and reference to the mentioned paper where I analyzed different, I called in this paper rural environmental monitoring, but the meaning is the same, rural or remote. And I analyzed them by their challenges and requirements and proposed some solutions. And one of the challenges is sustainability, which is a topic of my talk today. Of course, we need monitoring for environmental sustainability, but also the monitors themselves should be sustainable. And this is an AI generated image. When I put the prompt IoT and AI driven water quality monitoring, and of course this is the opposite we aim when we monitor the environment. We don't want to interfere with the environment in such extreme sense, of course. And to do this, to introduce to this topic, I would like to start with a scenario that I find very interesting. This is a EU project that I led in University of Vienna, and it recently ended, but we're still working on the topic of water quality monitoring. So in this project, there are micropollutant sources or any type of pollutant sources upstream in the river. And in the river network in downstream, we built measurement stations which collect continuous data, continuous water quality data from the river. And the challenge is these, as I said before, these are very remote areas and there is no cellular connectivity, there is no cabled connectivity either. So transmitting data through satellite is somewhat possible, but it's unreliable and also expensive. So the challenge is we cannot transmit real-time data continuously to a remote data center. And the solution we found was to use a nearby processing facility, use a nearby processing device. This can be as small as a Raspberry Pi, as I said before, an edge server that trains the model for the local section of the river. So this is what we call local watershed model. And we also have a remote data center with much more computational capacity, which models the whole river, which has a bird's eye view of the whole environment. So these two models periodically communicate with model updates going to the cloud server and updated global models coming back to the edge server. So this is somewhat similar to federated learning if you have experience with that. And one question might come that if you only want to detect pollutants, why do you need an AI model or a machine learning model? Because it's a binary thing, either you detect it or not detect it. That's true. But our goal is not only to detect, but also backtrack the distribution of pollutant in the river to predict its source. So we have a very complicated model of the digital representation of the river, where we can, based on the current measurements from hundreds of sensors around the river, we can pinpoint the potential source of the pollutant so that we can warn the authorities who can take precautions to stop the pollution. And this was motivated with several disasters recently, which caused environmental impact in Europe due to micropollutants being very hard to detect. So in these cases, the pollutants were detected like 5 days later, only after fishes were dead or mussels were dead, so the effects were visible. And in our system, we aim to prevent this kind of environmental disasters by sending an early warning system within minutes. So, as I said, we focused on also the sustainability of the this monitoring system and the processing system. And we go beyond energy efficiency, because energy efficiency is the first thing that comes to the mind, but there are other aspects beyond that. There are challenges with energy and network availability, and I said before, if you use battery life is a problem. You have to either maintain them or dispose of them. If you leave them in the environment, this is an hazard, of course. In harsh environment, battery life can be reduced. Frequent replacement might be needed. And of course, batteries usually contain hazardous materials as well. Another thing is hardware can become obsolete due to rapid technological advances. And again, you need to replace these devices, which might not be recyclable in these remote areas. Again, these systems may interfere with the wildlife behavior if you have too large infrastructures deployed them. For example, if you want to bring network connectivity, if you want a satellite dish to connect, etc. So one solution regarding energy could be energy harvesting, where we can, luckily we are monitoring water, which has a river, which has a continuous kinetic energy, so that we can use micro turbines in the river to generate energy for our devices. Yeah, that's so one of the solutions for energy and network availability is energy harvesting. For network availability, the solution was already mentioned, using nearby resources for processing in the local area network, and then communicating only the model updates, which are significantly smaller in size compared to raw data, of course. We also optimize the number of sensors we use, how many deployments we have, as I said, less frequent communication and more efficient processing. So I will touch a few of these topics, these solutions we have developed throughout the project. And the first one is minimizing the footprint of sensors and gateways. As I said, this is a part of the SWAIN project. What we did was a special planning of sensor deployment, and our case studies. Since this is an international project, we had partners from various countries in Europe, and our case studies were actually in Turkey, Ergene River, which is challenging in terms of water quality. It is the dirtiest river in Europe currently. And the main challenge is there is industrial development in the upstream, and in the downstream, the water is used for irrigation, for mainly sunflower fields. And the challenge is, if we cannot detect pollutants in time, the water will be used for irrigation, and the crops will be affected. And our second use case was the Kokemäki River in Finland. And the challenge there was that there was again industry using river water, and the water itself was used as the utility water in the city of Turku. And our partners had Finnish Environmental Institute was our partner, and their estimate was that if a pollution event happens, the water intake location is from 20 minutes to 1 hour, depending on the water flow, the seasonal water flow. So we have this amount of time to predict the source of the pollutant so that the water intake can be closed off. Yeah, so again, we want to avoid a huge number of sensors deployed, both based on cost and sustainability aspects. But we also want to maintain reliability and high data quality. Therefore, we have a multi-objective problem. So we need more sensors for data quality and reliability, but less sensors for costs and sustainability. And this is what we developed. It's a framework called GANS. It stands for the 4 modules of that were developed by different partners. We had a gateway placement model for the communication from sensors to the central data center. We have energy modeling module. We have sensor placement module and network modeling module. And the idea is start from an initial placement, because monitoring systems were already deployed in some of these sites. So we start with an initial deployment, we deploy sensors and gateways, and then evaluate their impact in terms of energy, network communication, data quality, etc. And then use column pivoted QR decomposition technique to improve the deployment strategy and propose new places for sensors and gateways. So here is an example from the Ergene River, where we had the initial deployment of, I think, 75 sensors, where we assumed was the initial deployment, and placed gateways to cover these sensors because they need to transmit their data in real time. And then run our optimization algorithm to reduce the number of sensors and gateways. And I think we reduced from 75 to around 30 with the same data quality, but with less impact. So then we achieved 60 to 73 fewer IoT nodes, but the detected number of pollutants and the detection quality remained almost the same. This translated to 60% energy savings, which is a rare resource, as I said, in remote areas. And here you can see our approach compared with other multi-objective optimizers. The red one is the QR decomposition, which achieved with 30%, with 30 sensors, as I said, almost the same number of micropollutants that are available in this data. So if there are no questions about this first aspect of sensor placement, I will move to the second part of my talk, which is about minimizing the communication overheads. Just a reminder that the communication happens between the measurement stations to the edge server, and then edge server to the cloud server. And this First part is a continuous communication in a wireless network in short distance. And the second one is a long distance communication that happens in either periodic or when needed as well. And this approach that we deployed here, deploying a part of the AI model locally and the rest in a remote data center, is called edge intelligence or edge AI. According to the definition of International Electrotechnical Commission, it is defined as edge computing with machine learning and advanced networking capabilities, or a less informal definition by a survey of edge AI. It is mentioned as, instead of entirely relying on clouds, edge AI makes the most of widespread edge resources to gain AI insights. And it usually has a three-layer architecture where the sensors has the most data, but the least computational capability. So they have the simplest model, whereas we can have an edge server in the middle with some of the data being available and somewhat more complex model. And then the cloud server has the least data, but the most intelligence or most computational capability. And yeah, so it's basically a trade-off between computational power and data transmission rates. In between edge computing and the sensors, we have higher data transmission rate but lower computational power, vice versa in cloud. And there are different ways of deploying edge intelligence. For example, the highest level could be deploying everything on the device. So there is no central server, everything is trained on the device. And inference is also on device, of course. But there could be, as I said, different levels. And in our case, we are in level 4, where cloud and edge are co-training. So the training happens in both modules, and inference happens at the edge, near to the devices. And this is the three-layer architecture that we used. We have data source nodes, edge nodes, and parameter server. In our case, there is no training on the devices. Devices are not, or data sources, they are not intelligent. They just transmit their data to the nearby edge nodes. And this is streaming data communication. The partial models are trained at the edge nodes, and periodically they send to the typically a cloud data center, which is called parameter server, which combine these partial models into a global model and broadcast them back to the edge nodes. So again, this is quite similar to federated learning. Although in federated learning, usually the communication is synchronous. In our case, it is asynchronous because of network difficulties. So I would like to give an example of a challenge that we identified in this problem that we named staleness control problem. This is about the staleness of the models deployed at the edge nodes. So below, you see some charts showing the accuracy of the local prediction models. And at the top, you see a timeline showing the arrivals of local updates from edge nodes to the parameter server. So let's assume at time t0, we had updates from 2 edge nodes, but 2 others are missing due to unavailability of network. There were some failure at the nodes, which is very usual in our case. So, and at the edge nodes, there is already a model deployed. And when this model is not updated with new data, its accuracy drops over time, so it gets stale. And one thing we could do is that at time t0, we can just decide that, okay, this is the information that I have. I will update my model with this amount of information. I will not wait any longer until more information arrives to the parameter server. And in that case, I will update the model at the edge nodes, and its accuracy is expected to improve, of course, with the more fresh model. Another alternative is to wait for another time, for time 1, which hopefully another edge nodes data will arrive. We don't know which one will arrive, and we don't know how informative this data will be. But if we wait enough, we will get one update. And then maybe with more data from 3 nodes instead of 2, we will have a more accurate model compared to the green one here. Sorry. Compared to the green one here, maybe our model will be more accurate. But the problem is we will have to tolerate the stale model for a longer period of time. And as you can expect, the third alternative is to wait even longer, get all the data, maybe have the most accurate model, but tolerate the stale model for the longest period of time. And the question is to decide in real time which of these options is optimal. And as you can imagine, the solution is whatever the largest area behind these curves is the optimal solution. And of course, we don't know these curves, and especially we don't know before these updates arrive. We don't know the arrival times and what kind of unique data we will get from each update. So there are a lot of unknowns in that problem. So yeah, as I said before, the problem can be formally described as the area under these two combination of these two curves. So the utility, in this case, we used accuracy, but you can use any utility function. Utility of the stale model from t0 to time tj. I think the times are wrong here for some reason. From t0 should be here. To time tj, where you make the switch to the new model, and then from time tj to the end of the current iteration. And in this case, you use a new utility function because you have a new model. And our hypothesis was that this point to make the switch is not fixed, but it depends on it changes in every iteration depending on what kind of updates we have, what kind of data comes with these updates. And to optimize it, we modeled the problem as a Markov decision process, which consists of 4 parameters, the states, actions, then state transition function, and the reward function. The states in our case are binary strings representing whether the updates have arrived from sensors or not. I'm continuing the same example before, although it's a toy example with only 4 edge nodes. We have 0, 0, 1, 1, which means 2 updates have not arrived, but 2 updates have arrived. And 2 are delayed. Then the actions we can take is push, which means we decide that this data is good enough to build our global model. So we broadcast it immediately, and this is the end state. Basically, our decision process ends here. Or we might decide to wait. And in this case, there are 2 possibilities. Either the update from sensor 2 might arrive, or from sensor 1 could arrive. And in this states, so the next state is defined as the Hamming distance of 1 to the current state, but always increasing, of course. We cannot go from this one to this one. And again, in these new states, we might decide to push or wait. If we wait, we go to the next final state where all updates have arrived and we can only push in that state. There's also a possibility that we choose the wait option, but we remain on the same state. That means there were some permanent errors or disconnectivity which caused our models, our partial updates not arrive at all. So waiting in this case is a waste of time, and you get no improvements. And to take this into consideration, we have a dynamic reward function. So the reward, when we choose the decision to push, the reward is the utility of the model that we have. So if it is accuracy, it is accuracy. If we decide to wait and the new state is a different one, so we waited and actually switched to a new state, the reward is 0 because we don't want to double count the reward. We only count the reward when we push. And if we decide to wait, but the decision, the state didn't change, so it's the loops, that means we get a negative reward, which is a penalty. And this reward function is directly proportional to the amount of data and the variety of the accumulated data so far. And it is inversely proportional to the time elapsed. And based on this Markov decision process, we implemented a Q-learning model. I will not go into the details of Q-learning, but it's a reinforcement learning approach, and we used a specific version called delayed Q-learning. And delayed Q-learning means the updates to the Q matrix is delayed until a statistically significant number of experiences is reached. And this allows us to have some theoretical bound on the convergence of the model. So our model is PAC learnable, actually, which means probably approximately correct. And again, the theoretical details of this are available in the paper. Yes, so we also used alpha parameter using for the trade-off between new information, updating the queue, and for the future states. This alpha is inversely proportional to the number of visits we made to this specific cell of the Q matrix. And here we see some metrics we collected from the Argene use case. Sorry, it's not an Argene use case. It's a different data set. Where we measured age of information, which means how fresh the collected information from the sensors were incorporated into the models. In terms of seconds, we saw that our model improved the age of information fastest compared to the other alternatives. So what we achieved here is comparable accuracy to core AI. So what we called core AI is traditional way of collecting all the data in a central location and then processing it in batches, but all data is there already. But in our case, some data were missing, some arrived late, etc. Still, we had comparable accuracy with real-time responsiveness. We managed to keep age of information under 10 seconds, which means any data collected from the environment or whatever were in the model, included in the model within 10 seconds on average. We also had low communication overhead. It was less than 1 update per minute. And this was the first paper to define this staleness control problem and the first solution for this problem also. So I will now move to the last part of my talk, which is minimizing the energy consumption. This part will be short, so I will not, I hope not to go over my time. Yes, so to minimize energy consumption, because our devices are battery powered, we used a couple of techniques, which I will mention. But before that, I need to tell you what kind of models we deployed in the river. And in this case, we used graph attention networks. So if you are not familiar to graph attention networks, they are similar to regular graph networks, graph convolutional networks. The only difference is we also learn what is called an attention mechanism that assigns a different importance to each neighbor in the graph, so that the model can focus more on relevant connections. And in case of convolutional networks, it is only the weight of the node, for example, number of connections that node has. In our case, this part is also learnable. And this is important for us because in our case, each monitoring station represents a node, and the water flows between these nodes in different volumes. And in this case, we can also learn this part from the water flow, how much impact on the pollutant concentration it will make, depending on, as I said, the water flow speed or volume. So to save energy, as I said, we use two different techniques. The first one is, and by the way, none of these techniques are invented by us. They are available in the referenced papers. The first one is DNN partitioning. And the idea here is that battery-powered devices can run a portion of the DNN model, which is split in two, and then the rest of the model can be computed in a data center. In this case, instead of sending the input data, which might be large in size, you only send the intermediate information. This is also called split learning sometimes. And the idea is that your data is private, and you also send less data to the cloud, and you use some of the processing power at the device. And in our case, some layers of the graph attention network were conducted on the Raspberry Pi, depending on the capacity of the Raspberry Pi, and also depending on the energy availability. Sometimes there was surplus energy at the gateways, sometimes not. And based on this, we redirect the rest of the computation to the cloud, offload the rest of the computation to the cloud. And this saves energy, of course, compared to processing everything at the gateway, obviously, but also it saves energy compared to sending all the raw data to the cloud. I know I said before it is not feasible to send all the data, but assuming that we have reliable connection, for example, we are nearby a city in that case, if we transmit everything to the cloud, this is also a very energy consuming task. And so processing a few layers on the source was more energy efficient in this use case. And the second method we implemented is called early exits. And in this case, we have a multi-exit neural network that attach many side branches, like showed here, to the conventional DNN. These enable inference to stop early at intermediate points if the estimated accuracy or confidence reaches a threshold. So, which means that after running the five layers at the Raspberry Pi, if the confidence is high enough, we even don't need to send anything to the cloud. We can just do an early exit. Of course, this is for inference. For training, we still need to send data, not data, but intermediate models to the cloud. But for inference, we can just stop at this point. So we use the combination of network partitioning or split learning and early exit DNN to save energy on the monitoring stations deployed around the river. So before ending my talk, I would like to give some take-home messages. We can now say that large-scale environmental monitoring is feasible thanks to developments in AI and IoT technologies. We can also say that a lot of optimizations are possible for sustainability, for long-term monitoring solutions. They both preserve AI performance, but also achieve sustainability. And then for future advancement in AI-driven environmental monitoring, we need interdisciplinary cooperation between AI researchers, engineers, policymakers, and environmental scientists. Thank you very much for listening to my talk, and I am open to answer